All right, let's get into it. Today, we're cracking open a case file on a fundamental mystery. Think of it like a scientific detective story, one that kicks off in the 19th century, but believe it or not, ends with the very device you're watching this on right now. We are going to unmask one of the most basic building blocks of our entire universe, the electron.
So to set the stage, you have to understand the huge question looming over all of physics back then. This was the big one. Is the world, at its core, smooth and continuous, like the waves you see on the left? Or is it kind of grainy, made up of tiny individual bits, like the particles on the right? And look, this wasn't just some philosophical debate. The answer was going to completely rewrite our understanding of reality.
For a really long time, the scientific community was pretty sure they had this all figured out. And for them, the answer was, without a doubt, waves.
And you can see why they were so confident. First, you had the powerhouse equations from James Clerk Maxwell. They brilliantly tied electricity and magnetism together into one single theory of electromagnetic waves. Then Heinrich Hertz comes along and actually makes and detects those waves in his lab. It was like a 1-2 punch that knocked out any other ideas. The conclusion was stamped as an established fact. Light is a wave, electricity is a wave, case closed. Or, so they thought.
But like in any good detective story, a case is never really closed if there's a weird clue that just doesn't fit. And a strange, faint glow in a glass tube was about to blow this whole thing wide open.
So here it is, our first clue. Scientists were playing around with these things called discharge tubes. Basically, they'd pump almost all the air out, creating a really, really good vacuum. We're talking about 0.001 millimeters of mercury. Then they'd zap it with a super high voltage source. And what happened? This weird yellowish-green glow would just appear on the glass. And nobody's wave theory could really explain what was going on.
Pretty quickly, the investigation zeroed in on the source of the glow. Whatever it was, it seemed to be streaming out of the negative terminal, the cathode. So, naturally, they called them cathode rays. And this is where the plot really thickens. A physicist named William Crookes comes out with this totally radical idea. He says, what if these aren't rays at all? What if they're a beam of tiny, super fast, negatively charged particles?
Now, saying these were particles was a direct challenge to the whole everything is a wave idea. So to settle it once and for all, what science needed was a showdown, a definitive experiment that would force these mysterious rays to show their true colors.
And that brings us to J.J. Thomson and his absolutely brilliant experiment in 1897. He built this device that basically fired a beam of these cathode rays through a gauntlet of electric and magnetic fields, set up at right angles to each other. By carefully adjusting the fields, he could steer the beam with incredible precision. It was like the ultimate interrogation of nature itself.
And the confession he got was undeniable. The beam bent and curved under the influence of the fields in a way that perfectly matched how a stream of negatively charged particles should behave. An electromagnetic wave just wouldn't do that. The verdict was in. These were particles.
But Thomson didn't just stop there. He was clever. By carefully balancing the electric and magnetic forces to make the beam go perfectly straight, he was able to calculate a crucial property of these new particles, their charge-to-mass ratio. Basically, it's a measure of how much punch, how much charge, each particle packs for a given amount of mass. And the number he landed on was absolutely huge, 1.76 times 10 to the 11th coulombs per kilogram. And here is the most incredible part. That number, it was always the same. It didn't matter what metal he used for the cathode. It didn't matter what tiny trace of gas was left in the tube. He got the same number every single time. And that meant something profound. These particles, which he called corpuscles, but we now call electrons, they have to be a basic, fundamental ingredient of all matter.
Okay, so the suspect was identified. But to really understand this thing, the detectives needed to build a complete profile. They had the ratio of its charge to its mass, but what were the actual values? It was time to quantify the invisible.
And this leads us to R.A. Millikan's ridiculously clever oil drop experiment around 1913. It's just beautiful. He would spray this fine mist of oil into a chamber, and these tiny droplets would fall between two electric plates. Then he'd zap them with X-rays to knock electrons on or off, giving them an electric charge. By tweaking the voltage, he could perfectly suspend a single droplet in midair, balancing the pull of gravity with the push of the electric field.
After doing this over and over, painstakingly measuring thousands of these tiny droplets, Millikan found something amazing. The total charge on any droplet was always a whole number multiple of one single fundamental value, 1.602 times 10 to the negative 19th coulombs.
He discovered the charge comes in little packets. It's not continuous. And he'd found the value of the smallest possible packet. He had found the charge of a single electron.
And with that last piece of evidence, the puzzle was complete. The logic was so simple, so elegant. Step 1, Thomson gives us the charge-to-mass ratio, E/m. Step 2, Millikan gives us the charge, E. Step 3, dust off your high school algebra, and you can solve for the mass, m.
And just like that, the case file on the electron was closed. We had the charge, thanks to Millikan. We had the specific charge, or charge-to-mass ratio, from Thomson. And from those two, we got the mass, an almost unimaginably tiny 9.1 times 10 to the negative 31st kilograms. The electron wasn't a mystery anymore. It was a known quantity.
So, we've found it, we've measured it. What's the next logical step for science and engineering? Well, it's figuring out how to use it. How do you get an electron out of its home inside an atom so you can put it to work?
Well, to get that, we have to picture what's happening inside a piece of metal. You've got this whole sea of free electrons just zipping around, but they're not totally free. As this diagram shows, if an electron tries to just leave the surface, the metal is left with a positive charge, which yanks it right back. It's trapped. You can almost think of it as being in the prison of the metal.
Now, to break out of that prison, an electron has to pay a kind of toll. It needs a certain minimum amount of energy to make a break for it. And that energy requirement, which is different for every material, has a name. It's called the work function. It is, quite literally, the price of escape.
And this is a fantastic way to visualize it. Think of the electron as a little ball sitting at the bottom of a well. The depth of that well is the work function. If you want to get the ball out, you have to give it enough of a kick, enough energy to climb all the way to the top and escape. So the big question is, how do we give it that energy boost?
Well, as it turns out, we've come up with 3 main ways to pay the electron's price of escape. We can do it with heat, we can do it with a really strong electric field, or we can do it with light.
This slide gives you a great side-by-side of the first 2 methods. On the left, with thermionic emission, you're literally boiling the electrons off. You heat up a metal filament, which gives the electrons so much thermal energy, they just leap out of that potential well. But with field emission on the right, you're using brute force. You apply a monster electric field, like 100 million volts per meter, and you physically rip the electrons right out of the metal. The spark in your car's spark plug? That's a perfect example of this.
And the third method, well, this one is the most quantum of all. It's called photoelectric emission. You shine light onto a metal surface, and a single particle of light, a photon, can slam into a single electron and transfer all of its energy in one shot. If that energy is more than the work function, then poof, the electron gets kicked right out. This is the whole basis of the photoelectric effect, a puzzle that helped lead Einstein to quantum theory.
And so our detective story comes full circle. It all started with a mysterious glow in a dark lab. Then came the meticulous detective work of scientists like Thomson and Millikan, and it all led to our modern ability to control and harness these tiny fundamental particles using heat, fields, and light. Honestly, mastering the electron is what built our entire modern world of electronics, and it all started because a few curious scientists refused to ignore a clue that just didn't seem to fit. Makes you wonder, what mystery are we ignoring today?